Let us start this lecture, a thought process from Thomas Alva Edison. Genius is 1% inspiration and 99% perspiration, which basically indicates that you may have your talent, what I call exergy or availability. Unless you work hard, you cannot really utilize that talent for the benefits of yourself and also for the society. So, let us re-look at what we learned in the last few lectures. Basically, we looked at reheat cycle, reheat Rankine cycle, regenerative Rankine cycle. Of course, before that we discussed about the superheated Rankine cycle. If you look at what we are doing, we are basically trying to find out ways and means of enhancing the thermal efficiency. Question arises, is there any other way of enhancing thermal efficiency? If you look at the basis of enhancing the thermal efficiency is basically to increase the temperature at which heat being added to the plant or to the cycle, and also heat being rejected in the condenser in this case. So, if we can lower the condenser pressure, eventually we can decrease the temperature at which heat will be rejected, so that we can enhance the thermal efficiency. But if we will do that, then let us look at what are the things we are gaining and what we will be losing in the process. So, if you look at earlier the cycle is 1, 2 and then 3, this is basically 2 to 3 is your heat addition, that is your Q in, and 3 to 4 is your expansion, and then 4 to 1, this is your actual cycle if it is operated with that. But what happened, we have now changed the condenser pressure, right, from P4 to the P4 dash, right. That means there is an extra work what we are getting, right. So, what is that extra work? Extra is basically 1, 4, 4 dash and 1 dash 1. So, this portion of extra work we can get by lowering the condenser pressure, right. But however, we will have to now add some more heat into that, like in the area basically x 1 dash, 1 dash, 2 and 2, 1 x. So, this portion basically will be giving some heat input, right. So, therefore, of course, we may gain more with this lowering the condenser pressure, but there will be associated problem. As I told, lower the pressure, then there will be leakage problem, that has to be properly sealed. Otherwise, what will happen? The atmospheric air in the condenser will be getting into if there is a small leakage somewhere. And then like it will be a very difficult for the heat transfer to occur, because this will be what to call not only the two phase flow and also the addition, then it will be causing some problems, right. And therefore, people restrict this the condenser pressure to the 7 kilopascal kind of thing. Of course, in some of the example we may be putting 5 kilopascal or something, but however, with the better technology one can lower as well, right. So, that is of course, the future this thing. So, I mean this is the another way what I told you just now, that lower the condensing pressure and you can get a thermal efficiency, because there is a work what you call higher work output, and therefore, that will be, if you look at the for the same input. So, the thermal efficiency will be higher, because why? If you look at the thermal efficiency is equal to W net divided by Q in. For the same Q in, you are basically increasing net work output, because the net work output is increases with lowering the condenser pressure, right. So, therefore, the thermal efficiency will be what you call higher in this case. So, if you look at till now what we have done is basically taken the simple and ideal Rankle cycles. I mean not only the ideal cycles. In that case, what we have done? We have basically considered the pump and the turbine to be operated isentropically. That means there will not be any losses in that. Is it really possible to have that? Certainly no. I mean like you cannot have operate a turbine or a pump, right, or any other component as a matter of fact, that without any losses. So, losses will be there, means there will be irreversibility, right, and irreversibility will be there. That means, if irreversibility will be there, then the process cannot be considered as isentropic, right. And beside this, we will be considering also that there will be losses in the what you call boiler pressure, because we know that the whenever the flow is taking place in a pipe, there will be some losses because of friction of the pipe, and then we are adding also heat, there will be also losses, right, and kind of things. So, therefore, there will be losses both in the boiler and also in the condenser. So, if you look at boiler is from 2 to 4, this region 2, 3 and 4, this region, there will be also losses. And we can look at what are the losses and other thing, but in this analysis what we are going to discuss now, we will be not considering any loss of pressure in case of boiler. That means, it will be remaining as it is, but in actual system there will be pressure losses, right. There will be also frictional losses, right, because of this thing friction, there will be pressure losses. So, therefore, that we are not considering here, but and so also in the condenser, this is your condenser, right, what you call this is your condenser, and there will be loss drop in the pressure. So, that also we are saying that look, it will be remaining what you call constant for our analysis, it is a simplifying. But however, in our analysis what we will be doing, that 4 to 5 dash is your ideal expansion, that what we have already considered isentropic expansion. 4 to 5 dash is your isentropic, right, expansion, right. But we are saying that is not possible, and because of losses will be there. Therefore, the real situation that the expansion will be non-isentropic, that is from 4 to 5, I have shown as a dashed line. Similarly, if you look at in the compression, this 1 to 2s is your isentropic compression. And 1 to 2, that is here, which has shown as a dashed line in the red, that is your actual compression, right. If you look at from this diagram itself, that for the pumping work, for increasing the pressure, you need to give more amount of work in actual situation as compared to the isentropic compression. Yes or no? Because like if you look at of course, you take temperature, but if you go to the enthalpy, that you will find the enthalpy change between the state 2 and 1 is higher as compared to the enthalpy change between the state 2s and 1, right. So, therefore, more work input should be given in actual situation as compared to the isentropic case, what we had considered for ideal Rankine cycle. In the similar way, if you look at the amount of work which is done by the turbine during expansion of the steam between state 4 to 5 dash is less as compared to the work done for an isentropically operated turbine. right. So, therefore, what you are doing, you are getting less amount of work in the turbine, and you are giving more amount of work to a pump for a real system, right. So, of course, if you look at that this from the second law of thermodynamics, we know that S2 entropy is greater than S2S, right, because of there will be irreversibility. So, therefore, if you look at this is your S2 and S2 and this is your S2S, right. And if you look at this 5, what will happen? This will be your S5 and this is your S5S, right. So, therefore, also the S5 is entropy S5 is greater than the S5S, means isentropic process. For isentropic process, entropy will be lower, and for actual process entropy will be higher, therefore, irreversibility will be there and there will be input. Now, so this is we call it basically real Rankine cycle. Of course, I would like to put that it is not real Rankine cycle, rather semi real Rankine cycle, because we are not considering the losses in the boiler and also the condenser. Okay. But in for our purposes, we will call it as a real Rankine cycle. And let us look at how we can analyze this thing, right. Because if you look at earlier what we are doing for ideal cycle, I will be knowing this point. I mean, it should be given to you either from the superheated steam table, pressure or temperature, or I can go from here from the condenser pressure and then do that, right. We have done in the example, first example when I took, I did other way around, where the superheated condition was not given, temperature was not given, right, but the pressure was given. So, let us say that it is given, that is this pressure is known, like 3 to 4 pressure is known and temperature is known from the superheated steam table you can get. And by getting this, you can because this is isentropic process, therefore, you will get 5S point here, and if I know this condenser pressure and saturated condition, if I know the quality of the steam here at 5S, then naturally I can get. And how can I get that? I know that S4 is equal to S5S, right, that is correspond to isentropy. From this condition I can get what will be the X5S, right. And then once I know, I will get enthalpy, and then I can get enthalpy here and then all other points. It is very easy to do that, right. But however, how I will get this a 5, because I need to know this entropy here X5, right, and also I should know the what is the quality, that is X5. I should know also H5, right. I cannot afford to say that S5, that entropy at state 5 is equal to entropy at 4. It is not possible, because it is an unisentropic process. So, how to go about that? How we will do that, right? For that, it is quite difficult, but what we will be doing? We will be putting other way around. We will be defining certain terms, right, by considering that if you look at H5 is greater than H5S, right. And therefore, of course, as I told, if I know this what you call H5, I can find out what is H5S, right. I can find out very easily. Fine. This I can find out 5S if I know this 5S, right. I can get, and how I will get this X5S? By using this condition, S4 is equal to S5S. So, I can find out X5, and this is known and this is known, I can find out. but even if I will do that, but I cannot find out H 5, right. And also we know that H 4 minus H 5, right, that is the actual work what you call done, you can say, is less than the H 4 minus H 5 s, right. That means, the work done by the turbine under real condition or the is less than the work done by the turbine under ideal condition, right. It will be obvious, I am like kind of thing. So, if it is so, then if I can find out a relation between that, how it is, then I can find it out. For that, what we will do, we will have to define a term known as isentropic efficiency, which is defined as work delivered by the real turbine, that is H 4 minus H 5, divided by the work delivered by an isentropic turbine, that is H 4 minus H 5 s here. And this efficiency is basically known as isentropic efficiency, because we are comparing with respect to isentropic conditions, right, which is an ideal case. So, if I know this, I know this H 4, I know this H 5, I know this, then I can very happily find out H 5, yes or no. So, but that means I should know this efficiency beforehand for this analysis, which you can I am like get from the other experiences. And similarly, for the pump, this is your pump basically, right. This is your pump is 1 to 2 s and 1 to 2, right, and S 2 is greater than S 2 s, and we know therefore, the S 2 minus H 1 will be greater than S 2 s minus H 1. What is saying? It is saying basically the work input to the pump will be higher than that of the or the work input to the real pump or the pump under real situation will be higher than a work input to the pump under ideal condition. So, therefore, we can also define in similar way isentropic efficiency for a pump is the work required by the isentropic pump, that is basically S 2 s minus H 1, right. This will be smaller one, and the work required by the real pump, that is S 2 minus H 1. So, similar way, if H 1 is known to you and S 2 is not known, S 2 s is known to you, and then if it is known to this isentropic efficiency, you can calculate S 2 very easily, right. So, this way we will analyze the real cycle analysis, Rankine cycles. And keep in mind that as the what you call work output from a turbine for real case is less than the work output in a turbine under ideal condition, and also the real pump or the pump under real condition takes more work input as compared to ideal. Therefore, the net work done will be what? Will be reduced for the same input. Therefore, the real cycle is always less than the ideal cycle. Therefore, the thermal efficiency of the real cycle will be always less than the thermal efficiency of ideal cycle. So, let us take an example to concretize our ideas what we have learnt just now. That is a 5 megawatt power plant operates on a simple real Rankine cycle. Here simple means I have not considered the reheating cycle or the regenerative kind of thing, a simple one, right. And the steam is supplied to the turbine at 5 megapascal and 673 Kelvin. It is similar to that what we had done earlier, right. And subsequently cooled in a condenser to 5 kilopascal. This is your 5 kilopascal and this is 5 megapascal, and temperature is T4 is 673 Kelvin. And isentropic efficiency of the pump is 75%, and that of the turbine, that is isentropic efficiency of an 85%, and we will have to determine the net work output per unit mass, thermal efficiency and steam mass flow rate, right. So, how to go about it, right. So, if you look at it is a similar manner, what we will do, we will basically know these 5 megapascals, and we can very happily find out this H4, yes or no, from the superheated steam table, right. So, if you look at solution, from superheated steam table at P is equal to 5 megapascal and temperature 673 Kelvin, I can get H4 is equal to 3195.64 kilojoule per kg, and I need also entropy. So, S4 is equal to 6.6458 kilojoule per kg and Kelvin, right. And also we can get the data for this point, that is for what you call from the saturated steam table, from saturated steam table at 5 kilopascal pressure, right. I will get as Vf, which is nothing but your V1 in this diagram, 1.005 into 10 power t minus 3 meter cube per kg. If you look at it, is a very small number, and Hf, which is equal to H1, because this is the saturated liquid point, is equal to 137.79 kilojoule per kg. Hfg is equal to 2423.66 kilojoule per kg, and we need to also know this Hg is 8.395 kilojoule per kg Kelvin, right. And of course, we can write down Sf, F, which is nothing but S1, this is 0.4763 kilojoule per kg Kelvin. Now, see basically if you look at we need to find out this point, right. If I want to find out net work output per unit mass, what I will have to do? We will have to basically find out net work output, that is nothing but your in actual system H4 minus H5, yes or no, for the real turbine, minus H2 minus H1. This is for the pump, this is for the turbine, this is for the pump, right. And if you look at H 1 is known to you, right, H 4 is known to you, H 5 is not known and H 2 is not known. So, how to find out? What we will have to do? We will have to basically find out the H 5. H 5 I can find out very easily. What is that? Isentropic turbine. What we know that H 4 minus H 5 divided by H 4 minus H 5 S. Yes or no? We have defined this and this is known. What is these values? These values is 0.85 given. So, H 5, that means H 4 is given. Now, we need to find out H 5 S. So, how we will find out H 5 S? I should know what is X 5 S, then only I can calculate, right. So, H 5 S, if you look at, can be calculated very easily if you know this quality at station 5 S. So, how you will calculate the quality? We will have to do isentropic process for isentropic expansion, that is 4 to 5 S. We know that is X, we know the S 4 is equal to S 5 S, right. And from that I can find it out and then I will get X 5 S will be equal to S 4 minus S F divided by S G minus S F. And this S F and S G at what pressure? That is corresponding to 5 kilopascal, this point, right. Right. And S 4 we know, this is known, right. This is your S 4. So, if you and S F is known, which S F? This is basically this S F, right. And S G is known, that is 8 point, let me put that number, that is 8.395. So, if you look at this is, let me put some number, then you will get some idea, otherwise I feel you people are not getting. 6458 minus 0.4763 divided by the S G, that is 8.395 minus 0.4763 and which is equal to 0.779, right. Once I get X 5 S, it will be very easy to find out H 5 S. So, then I can calculate by by knowing X 5 S, we can get H 5 S as H F plus X 5 S H F G, right. So, if you look at H F G is given, this is given, this is already we have evaluated, H F we have evaluated. So, if you just substitute these values, you will get 137.79, that is H F plus this is your X 5s, that is quality, into HFG is 2423.66, and we will get 202582 kilojoule per kg. Once we get that, we can get very easily H 5 is equal to H 4 minus turbine isentropic efficiency into H 4 minus H 5, what? It will be 5 S, yes or no, 5 S. So, therefore, we know these values, all those are known to you. So, if you substitute these values, you will get 2201.29 kilojoule per kg, right. So, what you can observe, right, H 5 is higher as compared to H 5 S, right, because this is 2201.29 kilojoule per kg, whereas H 5 S is 2025.82 kilojoule per kg, right. That means, it is not really expanded much, I mean like as compared to the isentropic process. So, now what we will have to find out? We can find out very easily what is the work done by the turbine, right. I can find out by the turbine in the real situation, right, very easily. But we need to find out net work done, right, okay, right. So, that we will have to find out now by looking at the pump. So, in the pump what we are doing? We are assuming the in the incompressible fluid, therefore, I can get very easily for this process for isentropic process. In the pump, that is 1 to 2 S, and that is H 2 S is equal to H 1 plus V 1 or delta P. So, if you look at that, we know this already, this is corresponding to V f here, right, this is known, and H 1 we already know at the this is your 5 kilopascal, right, this is your 5 kilopascal corresponding to that. So, if we substitute these values, you will get 137.79 plus this is a very small values 0.01005 of course into 5 into 10 power to 6, that is 50 megapascal and 5 kilopascal. You will have to be little careful about unit, and you will find out this is basically very small number, right, 137.79 plus 5.02 is equal to 142.81 kilojoule per kg, right. If you look at this change in the by the pump is very V 1 delta P is basically work input is very small. Now, we need to calculate basically H 2, because for the pump work is nothing but your S 2 minus H 1, but we do not know, we have just found out S 2 S. So, we will have to use again invoke that efficiency of the isentropic efficiency of the compressor, that is I c is equal to S 2 S minus H 1 divided by S 2 minus H 1, right. So, in this case if you look at H 1 is known, this is known, this is known, this is known. So, you can calculate very easily, that is equal to H 2 is H 1 plus 1 over eta c into S 2 s minus H 1, right. If you substitute these values, you will get 13779 plus 1 by 0.75 into 142.81 minus 137.79, and you will get S 2 is equal to 144.48 what you call kilojoule per kg. Actually, some people do not do this calculation, right, because they say it is very small, I will neglect it. I would suggest that do not do that in your exam, we may do in our calculation for sometimes, but do not do that. If it is given, please do that. Some people say that look, I have done this way, it is neglected, it is very, very small, tiny values, I need not to calculate. No, in your class, in the exam, you cannot afford to do that assumption, pump work, okay, I am saying. So, you will have to calculate, and also when you calculate, you will have a feel what you are getting. So, the W net, if you look at, is nothing but here H 4, H 5 minus H 2 minus H 1. So, we know this H 1 we know already, H 5 we have calculated, this is your H 5, this is your H 5, and S 2 we have just now calculated, this is your S 2, right. So, H 1 already we have evaluated from the saturated steam table. So, we can get that very easily, this one, that is 3195.64 minus 2201.29, that is your turbine work, minus 144.48 minus 137.79, you will get 987.66 kilojoule per kg. And if you look at the compressor work is very, very small, I mean you can see this is your, I call pump work, not the compressor work, pump work, okay, and turbine work is very large. So, the thermal efficiency you can evaluate very easily, that is W net divided by the Q in is equal to W net H what you call 4, that is your H 4, right, minus H 2. This is your work input or not, sorry, heat input or not, this is your heat input H 4 and S 2. So, this is I mean known to you, this is 987.66 into H 4 is your 3195.64 minus what you call H 2, H 2 already we know, that is your 144.48. So, you will get 0.3237 is equal to 32.37 percentage. But if you do this ideal cycle, this is the real cycle, okay, real cycle. But if you look at ideal cycle, right, what it would be? It will be something 38.4 percentage. If you look at, there is something around 6 percentage you can say decrease in the what you call real situations, in the real engines, real power plant. But keep in mind that it will be much lower, because we have not considered the losses in the boiler and also the condenser. Okay? We have only considered the losses in the compressor pump and the turbine. Okay. So, but we need to calculate another point, that is the amount of steam produce to produce 5 megawatt power plant. So, that is a very easier thing to do, because we know this power. So, that is power divided by the net work input, right, W net, right. That will give me, power is basically 5 megawatt, 10 basically 5 into 10 power to 3 kilowatt divided by the work net. Work net is 987.66 kilojoule per kg. So, I will get something 5.06 kg per second. Now, this is a real situation for real engine, real power plant. But in the ideal case, what it would be? Will it be higher or will it be lower? It will be lower for the same work, same power level, because this work input or the net work done basically will be higher. So, therefore, the amount of steam whatever will be consumed this or the being utilized is lower. So, if you look at that the steam will be basically increase for the real cycle, the change in the steam flow rate will be something 18.6% difference will be there, right, if you do for the ideal and real and compare and then do that. So, what we have seen here that we can analyze the real cycle by considering the losses through a little indirect way, by considering the isentropic efficiency for the turbine and the pump, and in some cases we may consider also the losses in the boiler and condenser, then efficiency will be much lower than the ideal one. So, we have learned basically about the what you call Rankine vapor cycle, Rankine cycle, right, and both reheat, regenerative and also the superheated Rankine cycles. Keep in mind that we have considered those things are for the ideal, but that can be also analyzed using this real cycle analysis what I have discussed just now for a simple system, right. There might be several ways of also enhancing the thermal efficiency of the steam power plant, right. Is there anything coming to your mind which we can utilize? For example, like some of the heat being rejected in the condenser. Now, if in an industry I need some steam or something on the lower this thing, I can use the heat. So, I can combine the power plant with the heat input, then I can utilize that thing, then we can have a total efficiency will be very high. There is a several ways and means of doing, and we call it as a co-generation, like we will be generating both the power and the heat. So, that co-generative power plant one can think of, and that is being used in western countries. I think in our country we will be using that in some of the industries in modern time, recent time people have adopted the co-generation. There will be several other ways of doing, like what you call combined cycles, right, where you can take this heat and use it, or you take the heat from another cycle and then use for generating the steam and then run the power plant. That is known as combined cycle, two cycles you can combine and get that thing. So, there are several complex systems people have developed to improve the efficiencies. I will not be discussing all that thing, because that is not a part of your course, but however, I will encourage you people to look at the interesting and very complex cycles what people have adopted in recent time to enhance not only the thermal efficiency, but also the reduce emission. So, that is also another aspect one can be done, and will this I will stop over. In the next class we will be talking about gas power cycles, and then we will be discussing about it. Thank you very much.